screen. Now have the...
Okay.
Yes, thank you. And okay, let's start with the course this afternoon. The last talk. So the lecture 3, the title of the lecture 3 is From Least Squares to the Kalman Filter, Particle Filter, and Beyond. And this is our pleasure to have the Dr. Horador Corpus Fellow, and who come from the National Institute for Space Research in Brazil. And let me see. Okay, yeah, and Dr. Horador received his PhD degree in the mechanical engineering on computational fluid dynamics and nuclear reaction physics in Federal University of Rio Grande do Sul in Brazil. And he was the visiting scientist in the Institute of Commerce Geophysical in Italy in 1997, and in the Department of Atmospheric Science of Colorado State University in 1998. Now he is a senior researcher of National Institute for Space Research in Brazil. He was the associate director at his institute during the 2008 to the 2010. And his research interesting most focused on the inverse performance, turbulent parameterizations, data assimilation, and scientific computing. And he and his colleagues received an award from the Kalman Academy of Science at 1916 for his work, Artificial Intelligence and Data Mining Applications to Photo Diagnosis and Parameter Estimation, and also got another award in 2021. And this is our pleasure to have his be with us today and give his talk. Thank you very much. And Horador, please.
Okay, thank you, Fan Xingfang. Thank you for the introduction. Thank you to agree to organize this course on data assimilation, and thank you for our audience. As Professor Fan Xing already mentioned, the title of my talk here is From the Least Square to Kalman Filter and Beyond. Let's go to start our presentation. And so the outline, I'm going to show to you some personal research interests in data assimilation, inverse problem, turbulence modeling, and drones, aerial drones, autonomous navigation. This is a cooperation between my institute and IEAV. This is Advanced Student Institute here in this town in São José dos Campos in Brazil. And then I'm going to talk about the estimation theory, introducing the least square method. And after that, I'm going to do some introduction about Kalman filter. And basically, this is a kind of approach that combines least square method and Gaussian statistics. Because this Kalman filter, there's a very computational intensive algorithm, and so we try to address how can you reduce in computational effort in this approach. And then I'm going to talk about particle filter. That is the some approach beyond the Kalman filter. And but Kalman filter and particle filter, you can think about this algorithm as a Bayesian's different filters, but using the same framework based on the Bayesian theory. And then I'm going to talk about beyond particle filter. I mean beyond the standard particle filter, because we continue to use a particle filter but a different approach. So I'm finished my presentation just to do this new kind of particle filter. and I'm going to show you how can you do that. And then my research interest is inverse problem, and this is one theoretical issues like a unified regularization theory based on the maximum non-extensive entropy principle. This is published in a journal, Brazilian Journal on Applied Math. And another, in practical application, this is damage detection in aerospace structures. And for example, if you try to identify some damage in space stations, we published some of our results in this Acta Astronautical Journal. Another is this is in a cooperation with Roberto Pinto Souto and Stephanie. This is a 3D tomography for ocean chlorophyll. This is a kind of inverse problem that this in the type 1 water. Type 1 water means offshore sea water, and in this ocean water, you try to identify some optical properties. And in these optical properties, you can apply the bio-optic approach, and then the chlorophyll profile is linked with these optical properties. And then you can, our job is try to identify the concentration of chlorophyll inside of the ocean. And so you can see here different layers of reconstructing the chlorophyll concentration in the ocean. Another interesting inverse problem is try to identify some profile properties in the atmosphere. For example, atmospheric temperature retrieval using a neural network. But using neural network, you can migrate this algorithm for FPGA. FPGA, it's a reconfigurable hardware. And so this hardware you can use inside of our radiometer, and this radiometer could be inside of the satellite. And then this is we call it intelligent radiometers. The intelligent radiometers not only provide the radiance that measured radiance, but also the profile that we are interested. In atmospheric turbulence, we try to identify some parameterization for different conditions of the turbulence inside of atmosphere: convective layer, boundary layer, residual boundary layer, stable or nocturnal boundary layer, and try to derive some parameterization for these different conditions in a planetary boundary layer. And this is our results using the Taylor turbulence modeling for atmospheric turbulence. And also you can apply the same theory to identify or to parameterize the turbulence inside of the clouds. And also this transitions boundary layer, imagine that we are diurnal boundary layer and change to nocturnal boundary layer. How can we do that? Or from nocturnal boundary layer to convective or diurnal boundary layer. And so you can apply the theory using this the same physical approach to derive new parameterization for that, and forget about physics. And if you are only looking at the data, you can also derive some parameterizations just using only data. And another interest is drone autonomous navigation. Why? Because we are dealing with an environment that depends on the sun activity. And so the solar activity impact our magnetosphere, perturbing our ionosphere. As you can see, for example, auroras, this is a phenomena that's coming from very energetic particles. And so there is a precipitation of these energetic particles over the poles. You can reproduce this in the lab. And ionosphere, well, Carl Friedrich Gauss, he has postulated that one electric conducting region in the atmosphere could be account of the observed variation of the Earth's magnetic field. Oliver had sight in 1902. He proposed the existence of the layer by which radio signals could be transmitted around the Earth's curvature. But in 1924, Edward Appleton provided the existence of the ionosphere. Because this, he got his Nobel Prize in Physics. And then, similar to what happened in meteorology or oceanography, you can also use mathematical equations with time evolution in order to predict the concentration, the electronic concentration in the atmosphere. And we do that here in Brazil. And this is our paper reporting first results of operational ionospheric dynamics prediction for Brazilian space weather problem. And on the top here, you are going to see different times in the day for the electronic content. In the bottom, these observations of the total electronic content, and that is March 2011, June 2011, and during the summer in the South Hemisphere, December in 2011. You can see that our prediction it's close or similar that we can observe it, but over the equatorial zone, there is this equatorial ionospheric anomaly. That is the majority production of ions for the atmosphere. It's happened from this region here. Okay, and this kind of scintillation we are going to call ionospheric scintillation. This ionospheric scintillation caused some troubles for GNSS signal traveling. And so this GNSS is a General Navigation Satellite System. For example, GONASS from Russia, Galileo from Europe, and GPS from the United States. And so due to the ionospheric bubbles and equatorial ionospheric anomaly, well, you can trust in GNSS signal. And so the idea is to use some alternative using image processing. I'm not going to talk in many details about this. And another interest that I'm dealing with is data assimilation. As you know, we have the observation system. Observation system, you are going to collect some measurements from the atmosphere, from the ocean, from the ionosphere, and from satellites, radar, surface station, and collecting data from aircraft to ships and whatever. And you are collecting all of this data for our computer, and you are going to combine this observation with the previous prediction. This is called background. And so combining these two sources of data, observations and numerical simulation from our prediction. And so you are combining these in order to compute the initial condition. And the initial conditions, this new initial condition, it's called analysis. And so the analysis is going to produce a new simulation, new prediction, in order to spread this information for the public. And this is roughly speaking, this is the cycle of the data assimilation. And so the data assimilation is the better approach in order to combine the observations and the background for producing the best initial conditions for our prediction. Professor Alberto say that there is three different applications: filtering, prediction, and smoothing. And this here we are trying to identify the best initial condition for the prediction process. And this is very interesting results from ECMWF, European Center for Median Weather Forecasting. And you can see here it's a performance, the skill of the prediction for 3 days in blue, in the blue region here. In the red region here, it's the prediction for 5 days, and the green region here means the prediction for 7 days, from 80 up to 2005. Okay, and you can see here in the top, imagine that you are watching the blue region here. And so in the top of this blue region, it's the skill for North Hemisphere for the ECMWF model. And then the bottom of this blue region is the skill for ECMWF model for the South Hemisphere. You can see here in the 80s, there is some 70% of agreement in terms of prediction with the real world. However, for the North Hemisphere, we have 85%, and so there is a gap in terms of prediction performance for the same planet using the same model in the same computer. Why? Because there is much more data at that time for the North Hemisphere to the South Hemisphere. And so according to, okay, there is evolution in terms of better parameterization, but a finer resolution for our computer model. But essentially, you are going to improve the acquisition of the observations. And so you can go to see the difference of the skill for the North Hemisphere to the South Hemisphere. It's going to be smaller and smaller and smaller. Up to 2003, for example, there is no difference of the skill between North Hemisphere and South Hemisphere. Why? Because we are increasing this observation system using satellite data. That's it. And so the people from ECMWF, Peter Bauer, Alan Thorpe, and Gilbert Brunner, they write this paper in the Nature, the journal Nature, in a review, the quiet revolution of numerical weather prediction. And you can see here that nowadays you are trying to use not only 3, 5, and 7 days ahead for prediction, but also you start to predict for 15 days ahead. This is the gray color here in these two curves here for North Hemisphere and the South Hemisphere. And so you can see here that for the 15 days prediction in this time scale, 15 days, there is no much difference between North Hemisphere and South Hemisphere. Okay. And so in terms of methods for data assimilation, we have a Newtonian relaxation nudging. For example, Didier Roux showed to us in previous presentation here one improvement in this nudging approach. Statistical optimum interpolation, Kalman filter, variational methods, 3D and 4D, and new methods for data assimilation, considering ensemble Kalman filter, vertical filter, hybrid methods, and artificial neural network. Okay, Newtonian relaxation, this is a topic of described by Didier Roux previously in previous talk from today. And also we use this approach for our scheme for ionospheric dynamics. You use this approach. I mean, approach presented today by Didier. And so I think that I need to talk a little bit more with Didier Roux to if you can apply his approach for our ionospheric model here. But let me to introduce the least square. The goal is to try to identify the law associated to the process under study. And so, for example, we try to identify the stiffness here. According to the Hooke's law, and so the force of deformation here, F, is associated to the deformation, X, okay? And you can measure this. Just you have a string here, and so you have a force F, and this force F is going to implies in a distortion. It's of the string, and so you can measure this deformation of the string, and then this measurement, it's the red dots here in our plot. However, the blue line represents the theoretical model, and so in order to identify this blue line here, I need to identify the stiffness K. Okay, and so one idea is we have our theoretical model, beta 0 plus beta 1 multiplied by X. This is our model. How can you, deformation is related to the force according to Hooke's law. And so I try to identify these parameters, beta 0 and beta 1, by using least square approach. Least square means you are going to identify some parameters or some functions and some vectors just to try to minimize the difference between model and the measurements. This square difference. And so I try to minimize this square difference. This is pretty standard. And so you can minimize this functional in order to identify the parameter here. But minimize a functional means to compute the gradient of this functional when this gradient of functionals is equal to 0. Okay, and so some brief history about least square. Carl Friedrich Gauss has developed the method in 1795 by age of 18. The expression least square was introduced by Legendre in Appendix 9 method pour la détermination de l'ordre des comètes sous la méthode des moindres carrés. On methods, sur la méthode, there's one method of least square published in 1805. But also American mathematician Robert Adrian, he has published this paper. It's not much, I'm trying to identify that this is one concerning about this age, about the initial century here. But another more rigorous proof was given by Gauss in 1809 paper, Theoria Motus Corporum Celestium. This is the title of the paper from Gauss. And the least square was developed independently for different mathematicians, and this mathematician has contributed in a different parts of the theory. Okay, and so this is our problem here. Try to identify these parameters, and the gradient of this functional. It's you are going to derive the linear regression equations. And so you can compute the derivatives, and you can arrive in this set of algebraic equation and put in the matrix formula. And the idea is, how can I solve this? And then I can identify our two parameter here. Okay, and so this is a linear regression in least square estimation. Okay, and when you're dealing with more observations than parameters, and so we have more equations than unknowns. And for example, this is our cost function here, objective function. This is functional that you want to minimize it, and so you can apply the least square approach, and so we arrive in algebraic linear equations, and solve this algebraic linear equations, you get the solution of this problem. Okay, but one equivalent statement of this problem is try to minimize this functional here. And so I have a matrix multiplied by unknown vector, and y here is the observations. And so you can solve this, minimizing this functional. It's equivalent this algebraic equation here. And so this algebraic equation here is solved by using this under this red circle here. It's called the Moore-Penrose generalized inverse. So this is algebraic solution for linear least square estimation. Okay, and so you already know that I can estimate some parameter, but how good is this least square solution? Well, the answer is addressed by Gauss-Markov theorem. For a linear model, have zero mean, and these errors are uncorrelated, and this error have equal variance. The best linear unbiased estimator, blue, of the coefficient is given by least square estimator. And so this is a mathematical theorem according to this assumption here. And then this Gauss theorem, it's starting from this model here. Y is equal this summation beta j under j multiplied by x under I plus 1 noise. Imagine that the expectation of the noise is 0, and the variance of noise is already known. It's the sigma square. And so the proof is try to imagine that you have a different estimation for this coefficients beta tilde, and you are going to prove that beta tilde only it's minimal if there is an agreement, if the expectation of beta tilde it's equal to the true solution, and this only happen if this is one difference here. It's the D matrix here. Only if this D matrix multiplied by X, it's equal to 0. And again, we try to identify the parameter, the variance of these parameters. And so the variance of these parameters, again, it's just be identified because this matrix D multiplied by transpose D should be equal to 0. If not, we are not in dealing with least square solution. Okay, and so the conclusion is the variance of a new estimation exceeds the previous by a positive finite definite matrix D multiplied D transpose. And so this proves our scheme. And so we are going to apply, but not only two parameters, but multiple parameters. And so we have this is our theoretical model, linear, and you can see here epsilon means the noise that we are dealing with, the modeling noise. And then we are computing the estimation. We are not going to identify perfectly the beta term here, beta parameters. We are going to estimate this in a certain way. And so instead of beta, it's B parameters to be estimated. And the idea is the B parameters should be a good approach for beta real true parameters. And so we are trying to minimize the residuals between the experimental Y and this model Y. And so again, we're going to arrive in this linear equation. And after this linear equation, you need to derive the normal equation, but you need to transpose of this X matrix here. And this transpose matrix here you multiply in both sides of our linear equation, and then you can solve this. However, you can measure using different sensors with different precisions. And so how can you take into account these different precisions using different sensors? Well, you can already know about this precision, and this precision it's provided by the who is building up the sensor. And so the inversion of the variance associated to the sensor, and so you can take into account in a weighted least square. And the weighted least square, you need to take into account this inverse of the variance associated to the measurement equipment, measurement instruments. And so this is called weighted least square. Okay. And so after that, after to take this solution, this least square solution, you can compute the matrix M and the covariance parameters of errors based on this observation errors. And so the covariance parameter errors estimated from M, it's MB, and MB it's computed by taking account the inversion of this multiplication of matrix transpose X, weight matrix W, and matrix S again. All right, but if we are dealing with only one type of sensor, and so this matrices could be simplified. In this case, our covariance parametric error is simplified by this approach here. Okay, and so you can compute the confidence interval in terms of if you take into account only standard deviation, the double of standard deviation. This is 25% of confidence interval, and 99% of confidence interval. It's the estimation parameter multiplied by 2.5 standard deviation, and so. But and so we have weighted least square and recursive least square. Recursive least square means we have a set of measurements. One time ahead, we have another set of measurements. And so how can you iterate? Okay, you can the first estimation, and then when you have a new set of experiments, new set of measurements, how can you take in account the previous estimation? That is called recursive least square. And so here our estimation from least square, when you have this y experiment, this is y0, and the error between the two and the estimation b0 under 0 here is our covariance error. And so the covariance error is estimated that we already know here. This is matrix, okay? And so this is the covariance that you can compute. But then we have, after some time ahead, arrive new set of measurements. Can we take advantage from our previous estimation? And so that is the recursive least square. And so our covariance error from the measurements, it's this W. You have two W's from the first time and second time, and then you have two types of errors, and then you can compute the covariance matrix here again, and then you can take a normal equation, The normal equation is you can compute the new estimation B1 here using this formula here, and so you can identify the previous estimation here and the second estimation coming from this new set of measurements. Multiply by P1. P1 is computed from this formula here. Okay, and so this is the solution that you can compute by recursion procedure. And so this is our covariance estimation, and this is coming from the first covariance multiplied by a new data that we are receiving. And so the second estimation here is based on, in the first estimation, plus a multiplication of gain matrix here, and this difference between the previous estimation and the previous estimation combined with the new data. Okay, and basically the recursive formula will make the covariance error matrix, and then after that we have this equation to update it our estimation of parameters. Okay. Finally, the Kalman filter. The Kalman filter is an algorithm considered for one of the most important advances for forecasting and filtering to estimated unknown vector. And the measurements, it's going to arrive in different cycle of the time. And so you have some frequency of measurements arriving. Okay, and so we have some dynamical law. I don't have only measurement difference between model and measurement. No, now I have one dynamical law, dynamical equation, in order to imagine that y here means the time. And so I have one estimation for by, this is one time, and I try to use one matrix F in order to compute or to estimate in how this parameter is going to value in one time ahead. This is y plus 1 here. This is my notation here. Okay, and so I have the observation equation. This xy multiplied by is equal to y. Okay, and so I have this one additional equation, and this additional equation, it's our equation for prediction. And so how can I combine all of these two equations? Well, if I have three different measurements, I can combine all of this, and so I drop in a standard least square approach. This is according to Gauss, but according to Kalman, you are going to do something different. You are going to take in account this recursive least square. And so the difference between Kalman filter and recursive least square, this transition matrix between two states is not dependent on time for Gaussian least square. But the modeling error is not taking account for recursive least square. But here you are taking advantage because we already know the statistics about our process. Okay, and so for Kalman filter, I need to have one dynamical equation. This dynamical equation is forecast equation, and then you are going to compute the analysis. The analysis is coming from the summation of the prediction, forecasting, associated to one additional value. This additional value is equal the difference between observation and the prediction multiplied by a gain, and this P is called discrepancy function. And this is our how can you apply the Kalman filter. The Kalman filter, you are going to compute the forecasting and the error of this associated with this forecasting by computing this covariance PF. After that, you can compute the matrix gain, and the matrix gain it's computed by using this formula here. And after that, you compute the Kalman gain, and so you can update your estimation from your forecasting model. And so you are going to compute the analysis here. It's the step 3, update the estimation. And so the analysis here, it's x over a. It's equal the prediction multiplied by Kalman gain, multiplication between difference between observation and the forecasting. After that, I can update this estimation. We're going to identify the covariance error associated to this estimation of the analysis here. And then when I arrive other observations, I can restart the cycle here. But the problem is, I never comment about that, but who is this guy? This guy is the covariance matrix that identify the error, modeling error. Modeling error is the difference between the true state and the modeling state. This difference, how can I compute the true value? In order to compute this covariance matrix here, because I need to identify the difference between the model estimation and the true value. But the true, we never know. Actually, the true is untouchable. And there is some methods try to estimate this matrix here. One is to parameterize it. And this parameterization, well, there is different approach. One approach is proposed by Javinsky. Professor Alberto mentioned the Javinsky book from 1970. In this Javinsky book, Javinsky, he has proposed one method to estimate this covariance matrix. You parameterize it, and so you use it one secondary Kalman filter, because Kalman filter, as you know, this is one estimator taking account a statistics of our stochastic process here. And this statistics in this process is a Gaussian one. And so we are dealing with a stochastic process when you're dealing with Kalman filter. Okay, and so you parameterize this and you using a Kalman filter in order to estimate this covariance error of modeling. And so this covariance matrix for modeling, you can parameterize this. This is called the adaptive Kalman filter. And this adaptive Kalman filter, well, we are going to using a Kalman filter in order to estimate this matrix here. And we have used this. This is my first result publication in data assimilation using adaptive Kalman filter. Okay, and so you're using here in shallow water, one-dimensional shallow water equation for the atmosphere. Okay, one application of Kalman filter is in shallow water, two-dimensional shallow water for ocean circulation. And so we have a three equation here, two equations for velocity, one equation for the ocean height. And the ocean height here, it's considered linearize the equation using one average ocean height here. And so you are going to compute the deviation of the ocean height related to this average ocean depth here. Okay, and then well, this is we linearize all the equation, and you can derive this set of equations for the shallow water as modeling ocean circulation. I extract this modeling from this book here. This is book written from Professor Bennett, Inverse Modeling in Ocean and Atmosphere. And that is the boundary conditions, okay? And this is the parameter that we are using in order to have a good representation for ocean circulation using shallow water model, okay? All right, and so the green here, it's the estimation using Kalman filter. And in red, looking at here, there is some difference between these two approaches, Kalman filter and neural network. I'm going to comment in a few slides why you are using neural network. And I can see here the data for zonal wind, meridional wind, and ocean high, ocean deep here. And this is a zoom that the true is in the black line here, and this is the green is Kalman filter, and the red line here representing the data assimilation by neural network. Okay. But Kalman filter, it's okay every time? No. There is some assumptions. For example, sometimes we are dealing with a linearization of our dynamics, and mainly we are dealing or assuming the Gaussian statistics for modeling modeling errors and measurement errors. You are considering Gaussian statistics. For measurements, it's not so far from the reality, but modeling, it's hard to consider Gaussian statistics every time. And so another thing is if our observation is not so frequent enough, and so there is some kind of deviation between the simulation produced by our model and the dynamics dynamics itself by nature, atmosphere dynamics, ocean dynamics, whatever, okay? And so basically the statistics could be not Gaussian. Therefore, linearization could not be worked, and Kalman or Gaussian statistics cannot be applied. And so how can I do that? Well, you can apply it for the VAR or particle filter. Dr. Amos Lawless is going to talk about the data assimilation approach in tomorrow, and then I'm not going to talk about that, but as Professor Alberto teaches in this morning, in this afternoon, there is 3 types of operator here for prediction, filtering, and smoothing. Okay, as Professor Alberto already teaches about the difference between 3 procedures here, and so I'm not going to do some details. But Kalman filter and particle filters, they are a Bayesian strategy for filtering. And so we already know about the previous state of our dynamical system, and try to compute from observation. Z here means observations. You try to compute from these observations. We try to do some kind of prediction. And this prediction, we are going to do some setup by theorem and considering a Markovian stochastic process. And so Bayesian filters try to do some prediction and update. More about Bayesian filters you can identify in these 2 books here: Data Assimilation, Math Algorithms and Applications, Mark Ash, Mark Bucket, and Moel Nodet. and Everson Vospoil and Peter van Leeuwen, Data Assimilation Fundamentals. This is 2 books you can get much more information about Bayesian filters. But basically, a particle filter algorithm, you start with an initial ensemble. And this initial ensemble, you can compute one initial PDF distribution, okay? And so you are going to do a comparison between this distribution and the distribution from observation here. And so this difference between these 2 distributions, it's you are going to compute the weights. And this difference here, it's called likelihood function. In general, the standard, the most of algorithms are using this likelihood function here as a Gaussian one. Pay attention for this. And so after that, we have computed this Q, this is the weights, and so you are normalized it in order to have one distribution, statistical distribution here, and then we apply the resample and selecting what kind of particles you are going to deal with ahead. And someone is going to disappear. And so this disappear process, it's called resample. And then you compute, after this process, you are going to compute new particles, and the algorithm is going to repeat in a new cycle. Okay, pay attention for this. This is very important. When I talk about beyond particle filter, because I'm going to modify this likelihood function here. Okay, basically, resampling means we are going to disappear with this probability, low probability associated from some kind of particle, some kind of solutions. And then in order to maintain the population, the samples that we are dealing with, and so we are going to do some clones, between quotes, this word clone. You're going to do some copies with a little difference. The maximum probability solutions or part of our population, and so that individuals or particles with more probability associated to a higher probability, you are going to do some copies for this higher probability member of our ensemble. Okay, in particle filter, Peter van Leeuwen from Colorado State University is going to talk much more about that, and so I'm not going to do some detail, but again, pay attention for this operator here, likelihood function, likelihood operator. And so let me to move one step ahead. Everything is perfect? Well, in the distribution space, there are at least 2 attractors for stable distributions: Gaussian and Lévy alpha stable distributions. In terms of central limit theorem, you can imagine that we have a random variable, and this random variable, it's a result of the summation with different random variables, but each different random variable has it's uncorrelated to another ones and other ones, and also you are going to guarantee, it's one assumption, that all of these random variables has statistical moments well defined. But if you are dealing with statistically independent random variables, and you are going to do a summation in order to have another random variable, this random variable resulting from this summation, if this other variables has no well-defined or not defined statistical moments of higher order. And so the Lévy-Guédenenko central limit works. I mean, this random variable is associated to Lévy alpha stable distribution. And so imagine that in this box here, we are collecting all distribution possible. One attractor here, according to central limit theorem, is a Gaussian distribution. But according to Lévy-Guédenenko central limit theorem, there is another one, another attractor here. It's the Lévy distribution. And so my question is, how can I identify if you are dealing with a stochastic process linked, associated to Gaussian, that means standard central limit theorem, or we are going to dealing with a Lévy-Guédenenko central limit theorem? How can I decide this? That is my point. And so this is one Gaussian distribution, Cauchy distribution, Lévy distribution. By the way, this is a 3 example of stable statistical distributions, okay? But there is one interesting distribution. This is a distribution from Tisales. Tisales is a researcher that has proposed the generalized thermodynamics or non-extensive thermodynamics. And he developed one approach based on in this parameter Q. This parameter Q means non-extensive parameter. And this non-extensive parameter try to deal with non-extensive entropy. And this non-extensive entropy means for Boltzmann entropy, we can, in mechanical statistics, we have, for example, we have 2 systems. And if you put together these 2 systems, which is the entropy associated when you do this kind of union, this kind of summation of these 2 systems? Well, if the system 1 has entropy 1 and the system 2 has entropy 2, when you put together all of these 2 systems, the final entropy is just the summation. Entropy is entropy 1 plus entropy 2. According to Tisales, we have something else. This is non-extensive approach for thermostatistics. And so, according to Tisales, his distribution with the non-extensive parameter is greater than 1, and so you can get this kind of distribution. And when this non-extender parameter is less than 1, that is the distribution. And so, but one interesting here is, if this parameter is greater than 5/3, but less than 3, and so this distribution, it's in agreement with the Lévy-Guédenenko central limit. However, if this parameter is less than 5/3, we are dealing with a standard central limit theorem. And then, that is my idea using the Javinsky idea. Javinsky used the adaptive Kalman filter in order to compute, parameterize the covariance matrix here. My idea is I need to identify this parameter, this non-extensive parameter, in order to identify the best likelihood function for our application. And so, similar to proposed by Javinsky, I am proposed a secondary filter, particle filter, to identify the best value for this parameter Q. Okay, and so here you have the whole scenario. And so when this parameter Q is less than 1, we have this distribution. When this parameter Q is greater than 1, we have this distribution here. And if this parameter is going to equal 1, and so you recover the Gaussian distribution. And then that is the point. I can, changing this parameter, I can change from Levy distribution to Gaussian distribution. This is, at least, this is our two attractors inside of the space of the distribution. That is the point. And so our choice for using Gaussian distribution can be justified by central limit theorem. However, there is another attractor in the distribution space for some distributions that the second statistical moment there is no definite. This is the Levy-Gdenenko central limit theorem. And so for the case of the Thales distribution, we have Gaussian distribution if the parameter Q is less than 5/3. But you are going to have a Levy distribution if you are dealing with the Thales distribution with Q greater than 5/3. Okay. All right, and so we try to use the likelihood function using the Thales distribution, and the non-extensive parameter is going to be estimated by a secondary particle filter. You are going to test this with 2,000 particles. Okay, this is our prediction model. This mu t here representing the noise associated to model, and the observation system. It's also we have some this nu. It means the noise associated the observation equation. And again, when you dealing with a fixed parameter, parameter Q is equal 1.5 or 1.9. For Thales distribution, we have this error here, approximately 5 and 5.3. If you are using Cauchy as likelihood function, and so our error is 5.5. But if you use a standard particle, going to estimate it, the best value for the Q parameter, and then you can arrive in the last error, 4.5. Okay, and so this you are going to see Gaussian and new scheme here. And again, this is a generalized particle filter, and you can, if you are interested, you can adapt it. You can see here in this is a chapter in this book, Adaptive Particle Filter for a Stable Distribution. And we try to formalize from mathematical point of view using a key calculus. We try to prove that Thales distribution is a stable distribution, but we can. And so we do some formulation. And so I invited you, if you are interested in this theoretical stuff, please join us. And the question is, this distribution is stable or not? And to this kind of study, we are going to deal with characteristic function. Characteristic function is the Fourier transform of the distribution. And so we already know that the Thales distribution, when the parameter Q is going to 1, we recover the Gaussian distribution. But in terms of, but we already know about this limit here, and then using this limit here, you can identify this algebraic equation here, link it with exponential function, and so you can define our key exponential function using this algebraic formula, exactly the Thales distribution. Okay, And so you try to using define, instead of Fourier transform, using key calculus, the key Fourier transform and blah, blah, blah. And we define some mathematical difference using quasi field, and that we prove some mathematical new operation here. And then applying our definition, you can finally we can prove that the Q Fourier transform for what Q Gaussian is linked to Q exponential, and then we can prove that the Q Fourier transform of a Q Gaussian is also a Q Gaussian, and this is our statement for our key stable distribution. All right. And so, as I said, Peter is going to talk more about data particle filters, and let me to talk a little bit about how can I reduce the computational effort, because all of these schemes here, Kalman filter, particle filter, variational methods, and they are very intensive from computational point of view. And so how can you reduce this computational effort? We are going to show you some results using shallow water equation in 2 dimensions. Well, at least you have two strategies. You can modify the algorithm. For example, try to configure a neural network to emulate Kalman filter, for example. Or if you want to, you can use in different hardware architecture, and so you can explore different architectures for that. Okay, I'm going to show how can you emulate Kalman filter using neural network. And our approach, neural network is not, it's self-configuring by the self-configuring neural network is going to derive by using formulating as one optimization problem, and this optimization problem is solved by a meteorology called multi-particle collision algorithm, NPCA. Okay, and then our objective function here, we try to minimize this cost function here. This cost function here, we have a error from our learning phase in neural network. And we have a different set of data, and this different set of data is just to verify if after that you have some configuration, after that you have some weight connections for this neural network, you try to identify if this neural network has a good performance or not. This is where we can compute by using different data set, and we are going to call it this as a generalization error. And so you have 2 types of error here. One is training error, and another one is a generalization error. But including to objective function, we have a penalty term. This penalty term, it's because we try to identify the simplest neural network. Simplest neural network, it's a neural network have a minimum number of neurons and associated to a faster convergence in terms of learning phase. How many iterations I need to in order to have one a good set of weights, connection weights. Okay, and this for solving this objective function here, try to minimize this objective function here. We are going to apply this multi-particle collision algorithm for optimization in a high performance environment. This is Eduardo Luz, is my former PhD student, my colleague, he is retired right now, José Carlos Bettinelli, and myself, Haroldo Fraga de Campos Velho. We have tested this MPCA using this standard test functions from operational research functions. One of them is a Grievang function, And this is could be very simple. This is not so. This is a parabolic function. Yes, but close to the minimum point here, we have a lot of minimum, and so you can drop one of these local minima here, and then is try to overcome this local minima in order to identify the global minimum. Okay, and the standard scheme for the particle collision algorithm, well, the answer is not so good. But if you're using NPCA, well, you can get we are very close to the optimal solution here. Okay, and so our idea is try to identify the number of the hidden layers in our neural network. By the way, we are using supervised neural network, multi-layer perceptron, and the numbers of neurons inside of each hidden layer. Try to identify the type of activation function and try to identify the two parameters for the learning phase, momentum ratio and learning ratio, I mean. Okay, and there is the maximum number of you can, this is up to you. I mean, you can configure this, but we are using the maximum number of the hidden layers is 3. The maximum number of inside of each hidden layer is 32. The learning ratio, there is this interval 0 up to 1, and the momentum ratio, it's an interval 0 up to 0.9. And there is 3 types that you can use in other type of activation functions, but here you are using hyperbolic tangent, Gaussian, and logistic function. Okay. I'm going to show you some results using shallow water 2-dimension for ocean circulation. This is published this year. This is data assimilation by neural network for ocean circulation, parallel implementation. But the assimilation of ocean, we are only the observation here is the ocean depth, okay, the height of the ocean, and this is called Q variable here, and the exact value is this continuous line black here, and we have a dot points Kalman filter, and artificial neural network is this other point here. And so you can see here that neural network follow pretty well. In fact, the neural network is a little bit better than Kalman filter here. But Kalman filter and neural network has a good agreement with the true value. But there is a difference, more important difference. If you're collecting using 25 points of observations, and the second experiment here, it's collecting from 100 points of observation. Okay, and so using Kalman filter, you are going to expand in terms of CPU time 42 minutes. However, using neural network is 1 minute and 40 seconds. 42 minutes against 1 minute and 40 seconds. But if you are using 100 points for collecting observations, the Kalman filter expand in terms of CPU time 1 hour and approximately 20 minutes. And neural network, 5 minutes. 1 minute and 40 seconds and 5 minutes. That is a lot of difference in terms of CPU time. Okay, you can use neural network emulating Kalman filter in space weather. This neural network for auroral data assimilation, and this is our previous result here, published in Applied Mathematical Modeling, new approach for applying neural network in nonlinear dynamical model. Here again, with the neural network, it's trained, it's configured to emulating the Kalman filter results. This is other, but this is a little bit different. But also try to emulating the Kalman filter. But here we are using different approach for neural network. But also you can configure neural network to emulate variational methods, or particle filter. You can also configure neural network to emulate particle filter. And here you have on the left in your screen represent the data assimilation error using Kalman filter on the top. In the middle, particle filter, and on the bottom, it's variational method for data assimilation. On the right side, you can see the error for neural network emulating Kalman filter on the top. In the middle, the error of data assimilation using neural network emulating particle filter. On the bottom, you can see the error associated to error when neural network is configured as emulating the variational methods. Well, this is using algorithm approach for reducing the effort for our computation, but you can use coprocessor. Our coprocessor option is using FPGA. Well, if you're using coprocessor, the idea is to speeding up the processing, the processing for computation. But also FPGA, because we're trying to saving energy here. And you're using the Cray XD1 that we have inside of this computer for different nodes. We have 2 CPUs and 1 FPGA embedded in the same processing node. And here is our FPGA, and we have some using FPGA. For example, this is Gwen Choi and Wake Look from Imperial College, and also from Imperial, no, yeah, it's a computer department in the Pennsylvania State, and the Microsoft Research. It's this is a comparison for basic linear systems on FPGA, CPU, and GPU. But the point here, well, FPGA, it's a very more effective in terms of CPU time, but also one very important here is the save energy demand for the processing. The same processing by GPU and CPU, it's much lower energy demand when you are using the FPGA. It's more complicated in terms of the curve of learning using FPGA. It's you are going to get more time for your learning phase by programming FPGA than GPU or CPU. Okay, and that is what you have. We have rapid array processor, communicating processors, and FPGA, and we have this here. I'm not going to. The idea is to put the neural network for FPGA. There is some technical details here, but instead of computing the activation function, you are not using one kind of software to do that, but we put inside of the FPGA memory the table. And so we are going to use lookup table instead of to compute, because the idea is to reduce our computation, okay? And then this is one different, some technical details. How can you implement it using FPGA? And our approach, instead of to accumulate it or storage all of data here and then start to start the computation, the idea is to use a kind of pipeline algorithm to do that. And this pipeline, you can reduce the computation in terms of cycles that we are using between CPU and FPGA. And then the difference, but when you're using software and FPGA, the difference you can see here is very similar results, and the difference is very slow. The error is 5, 10 minus 5. But in terms of CPU time, software in terms of microseconds per cycle of data assimilation, it's about 120,000 microseconds, but using FPGA is 200,000 microseconds. It's 2 times, roughly 2 times slower FPGA than software. But take a look more in details about that. Transfer data from CPU to FPGA, it's about 1,000 microseconds. And transfer data from FPGA to CPU, it's about roughly 10,000 microseconds. But for processing time in the FPGA is just 2 microseconds. And so this shows us where we need to do some developments in terms of technology here, is try to minimize this time for transfer data from CPU and FPGA to CPU. It's not only for FPGA. All coprocessor has this bottleneck here, okay? But this time for processing is amazing, just 2 microseconds, okay? And the difference, it's in terms of when you're using neural network derived or designed by an expert, this is the error. But the error, it's much smaller when you are using some methods for automatic configuration, okay? And or I try to using another hardware using a photonic processor. There is this photonic processor is already in a computer. Is a JZA supercomputer in France. We are not using this. Just to mention, we are using the Cloud Light one. This is one account available to us. Okay, I think that I'm going to have some. We can apply this neural networks emulating not only Kalman filter but ensemble Kalman filter, and well, in other applications. One application is using global model from Florida State University. This is Rosângela Cinta, is a colleague of mine here in INPE, and Stephen Koch. Rosângela is a postdoc from 1 year under supervision of Stephen Koch, and some of these results using ensemble Kalman filter and neural networks is producing during this her postdoc with Stephen Koch. And regional model, atmospheric model, is also Vinicius Almeida is going to show us in some days ahead, okay? And well, you can using also neural networks for ensemble prediction. I'm not going to talk about this, and that's it. Thank you very much for your attention, and let me see if you have some addressing some comments, questions.
Hi, and thank you very much for your talk, and very impressive talk, and which covered the wide of the region of the data assimilation area, so from the least square to the Kalman filter to the particle filter. Especially beyond that, it's the adaptive Kalman filter and adaptive particle filter, and plus neural network and combined with the Kalman filter. and especially for the parallel computing used in the common filter and the data assimilation technology model.
Yeah, well,
the applications.
Marco Mazzolini had a question here. Is the model error not present in the least square estimation? That is the contribution of Kalman filter. It's taking account the statistics but also when you are going to take into account the weighted least square, also you can include the statistical from not our model, but also the statistics from your modeling. And so this is the contribution of Kalman filter. Okay, and so Peter Jan, least square estimation is done observation times. The model error is the error in the model equation that brings the state from the observation. Does that make sense? Let me hear again. The model error is the error in the model equations. The model error is the error in the model equation. Correct. That brings the state from the one observation time to the next. Yes, I think that makes sense. Remember that the Kalman filter has two parts. One, estimating state and statistical variance in the observation time. And two, propagating the state discoloration between the next observation. That's it. Okay, that's one important observation from Peter. And Peter, this is direct message to me. Okay, and this is because Kalman filter using that Kalman gain, this algorithm spread the influence of observations for other parts of the domain, not only close to the observation. This is spread the influence of the observation. This is a good point, and I didn't mention that. Thank you, Peter, to remember this. And yeah, and so I think that's a thank you, Peter, to mention that. And yes, this makes sense in the first question. Okay, so other comments or question?
And I have one question. So for the parallel computing, so you compile with GPU and FP, FPGA, and because the GPU will be very common method for the neural network. Do you think in the future which method will be very popular?
Yeah, good question. Well, I think there is GPU is today is more are using GPU as a coprocessor because first of all it's speeding up the processing for sure. Secondly, because all there is for in high performance computing, in general we are dealing with a two language, Fortran and C language, and the CUDA. It's the most used standard for codifying a CPU, a GPU. I mean, GPU from NVIDIA. But CUDA, it's a language very close, very similar to C language. And so all people that already know C language, there is no problem to use CUDA. And so I think that there is this is a very interesting component that people are. It's much more. You can find much more people programming using CUDA and GPU than FPGA. FPGA it's a little bit different. For example, CPU and GPU, it's a kind of von Neumann architecture. FPGA, it's not. It's another way to do a computing. And then this is another thing that you need to have another way to think, because instead of to use this sequential standard for producing your programming, your computer code, you need to think instead of this using state machine. And so the way to organize your algorithm, it's much more closed and easier to think about in terms of state machines than that algorithms for von Neumann architecture. And so there is two reasons in terms of how can your culture it's coming with us. One is dealing with architecture based on von Neumann architecture. Secondly, is the C language and CUDA language. And but today I think that you have a much more easy way to deal with GPU using OpenACC, because OpenACC using the similar standard than OpenMP. And then you don't need to use OpenCL or CUDA. You can use OpenACC, and this is much close to general for in parallel programming. But there is no OpenACC for FPGA. That's a problem. So you need to wait a better development for in order to have a better interface for CPU in terms of programming to connecting CPU and FPGA. There is today we have the VITIS. This is substituting the Vivado framework for deriving FPGA configuration. And so it's a little bit better, but it's not good enough, in my opinion. And so we have some cultural reason to block people to deal with FPGA instead of GPU. GPU, it's very close what we already done in terms of von Neumann architecture and programming using CUDA, for example. My opinion.
Okay, thank you very much. And very